If you have a circuit that uses a push button and you don't implement debouncing, your data could glitch and cause all sorts of problems. In this video, we'll build a VHDL push button circuit, debounce it using a state machine, and prove it all works using a 7-segment display. Welcome to the world of digital design. This is Metastable. Now, in order to create a debouncer, we'll first need some kind of push button circuit. Let's make a button counter that increases by 1 after each button push. We'll start by creating a new VHDL file called buttoncounter.vhd. At the top of the file, we'll include the IEEE library and the standard logic 1164 package. Our entity will define 3 standard logic input ports, which are clock, reset, and a push button. The clock is used to synchronize our logic, while the reset allows us to return the design to a known state. Both reset and button are active high inputs, meaning they read 1 when pressed and 0 when released. These signals come directly from the physical buttons on the board into the FPGA pins, where we can then use them to drive our logic. Within our architecture, we'll declare 2 signals, an integer button count and a standard logic button last. The button count signal will serve as our counter, keeping track of how many valid button presses have occurred. Button last stores the previous button input, allowing us to detect the exact moment the button transitions from not pressed to pressed. Without this, the counter would continue to increment for as long as the button remains held down, which isn't what we want. Setting up the button counter is fairly straightforward. We'll start by creating a clocked process. On each rising edge of the clock, we check whether the reset button is asserted. If so, we reset both the button counter and button last. Otherwise, we check that button is high and button last is low. When this condition is met, we increment the button counter. Finally, we update button last with the current button value. This means that the current button value will be usable as button last next clock cycle. At this point, we've created a working button counter, but our buttons aren't mapped to the FPGA. To connect our FPGA to external hardware, we'll need to create a copy of our basis 3 constraint file, which you can find in the description. We'll rename the file buttoncounter.xdc. Let's uncomment the clock and then scroll down to the buttons and uncomment the buttons button L and button R, which we'll rename button and reset. Now, if we generated a bit stream for the design, we would get this.
Huh?
We have no way of knowing if our counter is increasing or not, so we'll need to find a way to display our data. One solution is using the 7-segment display. The Basis 3 board includes a 4-digit 7-segment display. It's called a 7-segment display because each digit is made up of 7 individual LEDs, which can be combined to represent the numbers 0 through 9, as well as a few letters. There is an important trade-off when choosing the 7-segment display over the onboard LEDs. The standard LEDs on the Basis 3 are easy to use and work well for counting in binary, but binary values aren't intuitive to read. The 7-segment display, on the other hand, is much easier to understand, but requires more complex logic to drive correctly. To understand the 7-segment display, there are 3 main components we need to cover: the anode, AN, the segment seg, and the decimal point dp. The anode is a 4-bit vector, where each bit corresponds to one of the 4 digits on the display. Anode, in addition to the other 2 components, is active low, meaning a value of 0 turns on a digit, and a value of 1 turns it off. This means that when anode is equal to all zeros, all 4 digits are enabled, and when anode is equal to all ones, all digits are disabled. While this may seem counterintuitive, active low signals are common because they simplify the underlying hardware. Seg is a 7-bit vector, with each bit controlling one of the digit's segments. These bits correspond to segments A through G, as shown in the diagram, with A being the rightmost bit and G being the leftmost bit. Lastly, dp is a standard logic that controls the decimal point for the digits. However, it'll be set to off for the entirety of this video. Now let's add these ports to our design. With an understanding of the display, let's run some basic tests. For our first test, let's write a value to all digits. Now we could manually turn on the bits in the segment array But if we ever wanted to change the value displayed, we would have to go back and figure out the new bit value each time. An elegant solution to this problem is to create a set of constant values that map to the available numbers the 7 segments can represent. Constants are static values, meaning they don't change once the design is implemented. Constants are beneficial when we plan on using data repeatedly throughout a design. We can implement a constant the same way we implement a signal, except we use the keyword constant. Now we could create a constant for each value, or we could create a table that contains all of our constants. However, there is no constant array type, so we'll need to create our own. Creating data types in VHDL is actually quite easy. We can do it by starting with the keyword type, our type name, and then the definition of our type. So we'll write type 7seg is array 0 to 9 of standard logic vector 6 down to 0. This new type, 7seg, is a 2D array which has 10 elements from 0 to 9, with each element being a 7-bit standard logic vector. A common pattern for multidimensional arrays is to have the outer arrays using ascending indices to track element positions, while the inner standard logic vector uses down to notation to track the orientation of the bits. Using down to means our rightmost bit is the least significant bit, whereas the leftmost bit is our most significant bit, which mirrors how we read decimal numbers and feels more intuitive. Now let's implement our new type. We'll create a constant segval with the type 7seg. From here, we'll list the values for each element. For instance, if we reference the segment diagram, our first element 0 is associated with the binary 10000000. We use double quotes for all data displayed in arrays. The capital B in front signifies that the array is explicitly binary. We'll do this for the rest of the values. Now we can easily convert decimal numbers to their corresponding 7-segment value. If we wanted to display all 7s, we could write seg is assigned to segval 7, anode is assigned all 0s, and dp is assigned 1. With the display set up, let's get ready for hardware. We'll uncomment seg, and dp in the constraint file, and then quickly create a new Vivado design project. After writing the bitstream to the board, we should get this. All the anodes are turned on, and the seg value is displayed on all digits. But what if we want to display values that don't have repeating digit values? For non-repeating digits, we need to quickly shift which anode is on. If we do this quick enough, it gives the illusion that all the anodes are on concurrently. Now let's implement the logic that controls the anode and segment values. We'll add 2 integer signals, count and index. The index will control which anode is on, and the count keeps track of how many clock cycles since the last index switch. From here, we'll create a new process. Let's call it AND_shift. We'll check for a rising edge and then for a reset. If we reset, both count and index are set to 0. If not reset, we check whether our counter has reached a predefined threshold. This threshold determines how long a single anode remains active before we switch to the next digit. While this value can be adjusted, setting it too high will result in visible dimming or flickering of our digits. In practice, values below 100,000 should work. When our counter reaches the threshold, we reset it and increase our index by 1, unless the index is already at its maximum value, 3, in which case we wrap around back to 0. If the threshold hasn't been reached, we increment the counter by 1. This means each anode is on for 100,000 clock ticks, after which the next anode is selected. We have a process that controls the anode index, but we'll also need a process that assigns our anode and segment ports. First, we'll delete the previous assignments and then create our process, segDisplay. For a reset, AN and seg are set to their respective zeros. Otherwise, we use a set of case statements. Case statements work similarly to if statements, but instead of evaluating multiple conditions, it selects which block of code to execute based on a control signal. Each case option is based on the value of our control signal, making the logic easier to read and debug. For our case system, we'll use our index signal. For example, if we wanted to display the value 1, 2, 3, 4, then for the 0 index, we would write when 0, anode is assigned to 1110, and seg is assigned to segval of 4. We'll do this for the remaining 3 cases. At the end, we'll add another case for others, where an and seg are set to their reset values. This case is used if something goes horribly wrong and a case outside of the scope is assigned. We'll then end the case system and the process. Now this process should take the index value created in the AND shift process and use it to assign the correct values to our ports. If we run this on hardware, we should see 1, 2, 3, 4, which means we can correctly write to each anode in our display independently. Now it's time to connect our button counter to the 7-segment display. But how can we do this if our counter is an integer and each of our 4 digits can only handle values from 0 to 9? Well, we'll need to split our button counter into a set of 4 values, which we can then feed into a segment mapping table. The easiest way to do this is with a function. Functions in VHDL work similarly to functions in programming languages. They take in inputs and return an output. We have actually used functions before. Rising edge is a function. It takes in a signal and checks if that signal is transitioning from low to high, and returns a true or false. In VHDL, functions describe purely combinational logic, meaning their outputs are ready immediately and do not rely on a clock. Because of this, it's important to be mindful of how much logic we place inside them. Large or complex functions can create long combinational paths, which may lead to timing issues. Dividing our counter into 4 digits in a function will require multiple division and modulus operations, which can easily cause timing issues. Rather than performing these resource-heavy calculations every time the button counter changes, we'll run this conversion for all possible values once, before the design is loaded onto the FPGA. The results will then be stored in a pre-computed lookup table. At runtime, the hardware simply indexes into the table instead of performing the computations. For this function, we'll need to define 2 new types. We'll call the first type int array and define it using natural range of integer, which means the range is specified when the type is used, rather than when it's declared. The second type is called digit LUT type, where LUT stands for lookup table, not to be confused with the LUTs used internally by the FPGA for logic. This type is defined as an array indexed from 0 to 9999, with each entry containing an int array from 0 to 3, which represents the 4 digits of the display. With the types defined, we can now build the function. We use the function keyword to create generate digit LUT, which returns a digit LUT type. Inside the function, we declare variables, which are similar to signals but exist only within the function. Variables use the variable assignment operator, and their values are usable immediately, rather than waiting for a clock edge. Next, we'll add our variables. The first is our lookup table, type digit LUT type. The second is an integer temp, which we'll use to break the counter into its individual digits. After declaring the variables, we'll start the function with begin, and create a for loop that goes from 0 to 9999. Inside the loop, we first assign the current loop index I to temp. Then we extract the ones digit by taking temp mod 10 and store this remainder in the 0th index of the lookup table. Next, we divide temp by 10 to remove the digit we just assigned, and repeat this process for the tens, hundreds, and thousands digits. We will repeat this loop 10,000 times. Once the loop finishes, we return the lookup table and end the function. The result is a table containing every number from 0 to 9999, and an associated 4-element integer array, which we can use to easily feed into the segment mapper. Next, we create a constant, digit LUT, type digit LUT type, and assign it to the function we just created. Since it's a constant, all the digit values are ready to use when the design is loaded onto the board. Now, we'll finally connect our binary counter to the 7-segment display. To do this, we'll create an int array button count array from 0 to 3. We'll also create a process digit splitter that breaks the counter value into the digits. When reset, all digits are set to 0. Otherwise, button counter array is set to the digit LUT of button count. From here, we just need to change the seg assignment in seg display to match the indices. We'll also add a safeguard in our button counter process to avoid counting past 9,999. Not that it's likely to happen, but just in case. Okay, that was a ton of work for a 7-segment display, but the payoff will be worth it. Let's run the design. On hardware, this is what we get. When the left button is pressed, our counter goes up. If we press the button enough, though, we'll start to see glitches where our value goes up by more than 1. We can reset our counter with the right button, but we will continue running into random counting errors. This is due to voltage spikes when our button is pressed. Analog buttons are noisy, meaning their values aren't instantly stable, and can bounce rapidly between on and off. The code that we have doesn't account for this. To fix it, we need to implement a button debouncer. A button debouncer circuit makes sure that button inputs are only accepted if they've been validated. We'll implement our debouncer logic by using a state machine. So what is a state machine? At its core, a finite state machine is just a way to organize logic into a set of distinct states. A stoplight is a classic real-world example. It has 3 states: green, yellow, and red. The state changes when specific conditions are met. Green has a minimum time on, then switches to yellow based on a time limit or input from other lanes. Yellow waits a fixed time before switching to red. Red also has a minimum time and switches back to green once all conditions are met. There are 2 main types of finite state machines: Moore and Mealy machines. In a Moore machine, outputs only depend on the current state, meaning if you know the state, you then know the output. Moore machine states and outputs are fully synchronous, changing only on clock edges. In a Mealy machine, the output depends on both the current state and the inputs. Mealy machines can have outputs that change immediately in response to input changes, even between clock edges. This asynchronous behavior can introduce glitches and timing issues if not handled correctly. To avoid this, in this series, we'll generally stick to using either Moore machines or modified synchronous Mealy machines. For our debouncer, we'll be using a Moore machine. Now our debouncer will have 2 states: idle and pressed. When in idle, we wait until our button has been pressed. Once we detect it being pressed, we then start a counter and check back after a certain amount of time to see if we are still pressing the button. If we are, we switch to the pressed state. When in the pressed state, we set a debounce signal high to show our button value is stable. We then check for a button release. If our release counter reaches the max, we then set the state to idle, where our debounce output is 0. But with that understanding, let's build the design. Let's create a new file for our debouncer. Our ports will be clock, reset, button, and button db, our debounced output. We'll first create a new type for our state machine called dbState, which has 2 options, idle and pressed. Next, we'll add a constant integer countMax, which we'll set to 1,000,000 minus 1. This is the amount of clock cycles we are requiring the button to be on for a debounce to occur. This translates to 1/100th of a second using a 100 MHz clock. Next, we'll create our state machine signal state with an initial state of idle. Lastly, we'll create an integer signal count with a range from 0 to countMax. Moving on to the design logic, we'll create a clocked process with reset conditions that set our signals and outputs to their initial conditions. Otherwise, we use a case statement with our state machine signal. Case statements are how we can implement state machines in VHDL. From here, we can create our idle state. After this, we'll create our pressed state. And that's all for the file. From here, the last thing we need to do is create a debounce signal button db, implement our design in the original button counter file, and change our button counter process to use button db instead of button. We're now ready to test our design again. And here's the new design on hardware. No matter how many times we press the button, we won't get any skips or glitches. With that, you've successfully created a debouncing circuit. That's all for this video. In the next one, we'll learn all about FIFOs and build one on hardware. Leave a like if you enjoyed the video and subscribe to stay up to date. See you in the next one.